In this video, I'll talk about residual analysis for validating model assumptions for the simple linear regression model. So we're using our pizza restaurant example again, and we've fit the model with predictor population, student population, and response quarterly sales. And we've obtained the model estimates. We have the analysis of variance table, and we have R squared, and we have the standard error of the estimate. But before we can proceed and use this model for prediction or inference, we need to have some reassurance that the model assumptions that we're assuming are reasonable. And so the way that we do that, because the model assumptions relate to the errors, we will look at the residuals, which are estimates of the errors. And just to remind you what the assumptions are, there's 4 of them. The first one is called zero mean. The second one is constant variance. The third one is independence. And the fourth one is normality. So to start with, we're going to look at the calculation of the residuals. So calculation of the residuals is the difference between the observed y and the predicted y, which we're calling y hat. And remember, the predicted y is obtained from the estimated equation. So 60 plus 5 times 2 comes to 70 for this observation. And then 58 minus 70 comes to minus 12. So we can calculate residuals for all the observations, and then we can make a scatter plot with the residuals on the vertical axis and the predicted values, y hat, on the horizontal axis. And this is known as a residual plot or a residual scatter plot. And we can use this plot to assess the zero mean and the constant variance assumptions. And what we would like is for this scatter plot to look like a horizontal band of points with no particularly strong patterns indicating otherwise. It's a little difficult to do with such a small sample size, but let me give you some examples of how a plot would not look okay. So for example, if we had a whole bunch of residuals up here in the top left corner, and then a whole bunch of residuals down here at the bottom middle, and then a whole bunch of residuals up here in the top right, then the residual pattern would be kind of curved the way I'm tracing like this in a U shape. And that would indicate the zero mean assumption is being violated, because moving across the plot from left to right, the mean is not staying at 0. It's going from positive to negative to positive again. This plot does not do that. It doesn't have any particularly strong patterns as we move from left to right. So the zero mean assumption is fine here. Another pattern that would be worrisome is if the residuals here were all very close to 0, and then by the time we get to the middle, they're a little more spread out. And then by the time we get over here to the right side of the plot, they're really spread out, going the full range of the plot. That would indicate the constant variance assumption is questionable, because as we move from left to right, the variability of the residuals is increasing. And that's often described as a funnel shape, because it kind of looks like a funnel with the wide end at this end. This plot does not do that. It doesn't have any particularly strong patterns where it comes to variance. So the constant variance assumption is probably fine. The independence assumption, it's a little difficult to check, and it usually isn't a big deal unless we have time series data. So we don't have time series data in this case, so we're going to just assume for simplicity that the independence assumption holds. And then the final assumption is normality. And to check normality, we're going to calculate something called a standardized residual. So the standardized residual depends on something called the leverage. And the leverage is calculated using this formula. It's based on how far away the predictor value is from its mean. So we can calculate leverages for all the observations, and then the standardized residual is based on the ordinary residual, the leverage, and the standard error of the estimate. So we can calculate standardized residuals for all the observations. And then we can think that if the normality assumption holds, then these standardized residuals should look like they come from a standard normal distribution with mean 0 and standard deviation 1. And so we can create something called a normal probability plot, which is illustrated here, also called a QQ plot. And the idea here is on one axis, plot the standardized residuals. On the other axis, plot quantiles from a normal distribution, from a standard normal distribution. And then the idea is that these points should line up along a 45-degree line if the residuals are normally distributed. In this case, those are close enough to the 45-degree line that we're not worried. A worrisome pattern here would be, say, if we had a point up here, well away from the 45-degree line, or maybe over here, or maybe in the middle, there might be a bunch of points with a very curved pattern to them, going like this, well away from the 45-degree line. That kind of pattern would cause us to question the normality assumption, but in this case, as I say, it looks fine. So it's kind of difficult to create this plot. So this plot actually came from XLStat, and I'll show you how to get that now. So let's get XLStat, and we will model the data using linear regression. And my quantitative variable is sales. And my quantitative predictor is population. And let me just check everything is set up correctly. Don't want to do prediction at the moment. Don't have any missing data, outputs. You can leave that as it is, and charts, we'll just leave that as it is as well. Okay. Okay, so here's the results. Let me just make it a little bigger so we can see what's going on. Okay, we'll skip past all the output we've looked at before and go to these scatter plots down here. So the one I want to look at is this one. So this actually has the standardized residuals on this axis. We just put the regular residuals on this axis. It doesn't really matter, the pattern will look the same. And then we've got the predicted values y hat on this axis. So this is the plot that's equivalent to this plot here. And then let's try and find the standardized residuals in the output. So the first one, minus 1.0792. Okay, so it's in this column here. And XLStat actually calls that a studentized residual. It's not the correct thing to call it really. A studentized residual is something else, and we'll talk about that when we cover multiple linear regression. And then what it's calling a standardized residual here is not what we're calling a standardized residual. So I would ignore this and just focus on this, and remember that these are what we're calling standardized residuals. So if I want to create a QQ plot, I go to describing data and then normality tests. And I select the standardized residuals here. And it's going to give me a whole bunch of numerical tests, but I'm interested in a chart. In particular, I'm interested in what it's calling a normal QQ plot, and that's what we're calling a normal probability plot. Don't click this one, which is something else. And let's make it a little bigger. So there it is down there. There's our normal probability plot. Okay, so that's residual analysis for validating model assumptions for the simple linear regression model.